Welcome back once again to the Transistor lecture series. So in our previous lecture, we have discussed about the self-bias. Now in this lecture today, we are going to solve a numerical on self-bias. So the numerical is given like this. Problem statement is draw the DC load line and determine the operating point. Assume this is a silicon transistor. Further, find the stability factor if beta is equal to 50. Now, the given structure of our circuit is a self-bias circuit. By looking into this, we can find easily. So, here another important parameter is given, that is it's a silicon transistor. So whatever values of resistors are given, in addition to that another important parameter silicon transistor, that means VBE we should consider as 0.7 volts, and stability factor, for finding stability factor, beta is given as 50. So these are the important parameters associated with this. Now to find the DC load line, first we have to analyze the output section of this. So this is the output section, and in this output section, so if we apply KVL here, so what we obtain, that VCC, that is equal to drop across this, that IC RC, plus this drop VCE plus the drop across RE, so RE into IE. Now if you can remember, in our discussion of self-bias, we have assumed IE is equivalent to IC, since IB is very small compared to IC. So we can rewrite this equation as VCC, that is equal to IC RC plus IC RE plus VCE. So which implies VCC is equal to IC taking common RC plus RE plus VCE. So if we take the output parameter in the left hand side, that is VCE will be equal to VCC minus IC into RC plus RE. So this is giving us equation number 1, which is nothing but the output equation. Now from this equation we can find the two important values of DC load line. If we put VCE equal to 0, VCE equal to 0, then we find IC is equal to VCC by RC plus RE. So if we substitute the given values over here, so VCC value was given, VCC value value is not given here, so let us consider this as 15 volt. If nothing is given here, generally 12 volt or 15 volt we can consider, so it is up to us. So VCC let us consider as 15 volts, and RC and RE values are given 1 kilo ohm and 2 kilo ohm respectively. So we can put it here as VCC 15 volt, and this is 1 plus 2, that is 3 kilo ohm, so 10 to the power 3. So by solving this, we find that IC value is 5 milliampere. Similarly, in this equation, if we put the value of IC 0, then we find another endpoint of the DC load line, that is VCE equal to VCC, so that is equal to 15 volt. So that means if we draw the DC load line, which is the plot of VCE versus IC. So IC here is in milliampere and VCE is here as volt. So this point and this point we found as 0, 5 and this point is 15 0. So this is our DC load line. So first part of the problem is done. Now in this problem, another thing we need to determine, that is the operating point. So to find the operating point, we need the operating voltage and operating current. So operating voltage, to find this one, we need to analyze the input section. So this is our input section, and from the analysis of input section we can find V2, that is equal to VBE plus the drop across RE. So here we have considered IE, which is equivalent to IC. So we can write as IC into RE. So from here we can consider, since we are finding the operating value of the collector current, so let us give a name as ICQ, and V2 is what? It is the drop across R2. So we can say that V2 is VCC into R2 divided by R1 plus R2, that is by using this voltage divider network. So that is giving us VB, we have considered as silicon diode, silicon transistor. So this is 0.7 volt. Then RE is given as 2 kilo ohms. So 2 into 10 to the power 3 into ICQ. So substitute the value of R1 and R2. So R1 is given as 10 kilo ohm, R2 is 5 kilo ohm. Here R2 is 5 kilo ohm. So pause the video and solve this equation. So I have already solved it, so I am writing directly. So ICQ we are finding as 2.15 milliampere. So this is giving us the ICQ. Similarly, now if we substitute the value of ICQ in the output equation that we have found in the previous slide, so we can write VCE, or we can use this another term here as VCEQ, that is equal to VCCC minus ICQ into RC plus RE. So substitute all the values and simplify this equation. So we'll find that VCEQ, that value as 8.55 volts. So as a result of that, now we can draw the load line, DC load line. So this is IC in milliampere, this is VCE, that is in volt. So here we have 15 volt, so 15 comma 0 point, here we have 0 comma 5 point, and here somewhere we have the operating point, so which is ICQ is given 2.15 and VCEQ is given 8.55 volts. So it is 8.55 comma 2.15. So this is our 2.15 point approximately, and this is 8.55 point. So here we have found the operating point or Q point. Now next question was find the stability factor, and beta is given as 50. So for stability factor, earlier we have seen the stability factor for self-bias technique is given by this equation, where R0 is R1 parallel R2. So R1 R2 in parallel can write as R1 into R2 divided by R1 plus R2. So that is giving us 5 into 10 divided by 5 plus 10. So if we solve this, we can get R0 value as 3.33 kilo ohms. So now substitute these values. RE we have seen it is given as 2 kilo ohms. So substitute these values over here. Beta is given as 50. So S will be equal to 50 plus 1, that is 51 into 1 plus 3.33 divided by RE is 2. So both are in kilo ohms. No need to write 10 to the power 3 in both the cases. So here once again 1 plus beta will be getting it as 51 plus 3.33 divided by 2. So this value we are getting, and if we solve it, we find value of S is equal to 2.58. Just check this answer with the help of your calculator. So three things we have found here. First, we have drawn the DC load line, then we have found the operating point, then we have found the stability factor. So here this problem is complete. So we end the discussion here. Thank you.